So we look at other properties of Petr nets and look at how we can actually solve some solutions to get performance metrics from these Petr nets. So we look at some more examples like we had seen earlier. Okay. So let us consider a system where there are two machines that are in operation, right, and the default state for them is on state, okay, and with some probability of or some mean time to failure, these systems will fail and then they will be repaired and then brought back to the normal working condition, okay. So therefore this is the name of the one of the places, right. So we will have a two place Petr net, one is labeled on and the other is labeled off, and then we have two transitions, so transition 1 and transition 2. So transition 1 we will call this as T failure, and then the other is transition 2 which is T repair, okay. So this T failure, T repair could be exponential, could be instantaneous, we are not right now talking about that. We have two places, two transitions, and from the on state, right, it is possible that you will go to this failure state, and then likewise some so when you fail then the particular machine is in repairs, has to be fixed, therefore it is in the off state, and then whenever there is a token in the off place then the repair process will start for that particular system, it will get repaired, and after finishing the repair it goes back to the on state, okay. So this is the general this is a set of transitions and places, right. So on place, off place and two transitions, okay. And this T failure would be the mean time to failure, that is what it means, right. So initially you will have some number of tokens in the system, and so every T failure time units you will end up essentially failing one of those two units, and then it will go to the off state, and then T repair is again the mean time to repair that particular unit. After finishing the repair it goes back to operational state, okay. So the number of tokens in the system could be anything, right. I could have 10 machines, 20 machines. So in this example we are simplifying it by saying that there are only two machines in the system, therefore the initial state and both of them start in the on state, right. Therefore so what is the initial state? What is the initial state? 2, 0, right. There are two machines, both are on the on state, therefore that is this 2 corresponds to that, and neither of them is in the off state, so that is the initial. So we will have okay. So that is the two tokens that are currently in the system, both are on the on state, okay. So this is now the system description. Okay. So if you look at the system state space, right, how does the system now move? So we have what are the possible states of the system. So the state of the system here is defined as the number of units number of tokens present in each of those two places, on or off, right. So what are the possible, so we let state, right, or the marking of the system, right. So let the state of the system at time t, it is simply the marking, right, be the m of t, right, marking of the system at time t, or marking of the Petr net at time t, right. So what are the possible system states now? There is 2, 0, 2, 0 represents one state, okay, and then we have another state which is 1, 1 where one is off and one is operational, or the third possibility is both are in the off state, therefore right both of them. So or sorry, one is on and one is off, and therefore the one of them is operating, one of those is under repair, okay. So then the if you look at this as a continuous time Markov chain, we look at the state transition probability matrix, right. So we look at the rates, I think you will have to go back and recollect your continuous time and discrete time Markov chains. So we represent the rate of transition from one state to another state. So the rate of transition would be, assuming that this is exponential, would be simply the rate at which we will go from this state to this state is with the rate T failure, and likewise the rate of transition from 1, 1 to 0, 2 is also T failure, okay. And likewise from 0 to, which means both the systems are currently not working, as if one of them is getting repaired. So when the repair gets finished for one of them, you will go back to one operational, one under repair, and the rate of transition for that is again T repair, and here one is operational, one is under repair, and therefore we go back to, after the repair is completed, we will go back to 2, 0, right. So this is called, this is your, the rate of transition from 11 to 20 is T repair again, okay. So this is how we represent the marking, right. So now we have a graph, right, we are looking at a graph, we will define this formally just in a minute. We have a graph that connects the different markings of the system and the rate at which you are going to move between this, or rate of probability of movement between those different markings, okay. Any questions on this part? Okay. All right. So now let us, so we talked about a Petri net having an initial marking, right. So the Petri net is defined, some Petri net is defined as consisting of the set of places, set of transitions, the input information for all the transitions, output for all the transitions, and we also specified this initial state of initial marking of the system, right. So that is what defines. So now we will have some more definitions. So some marking B, right, we will call this some marking, say, or MB, right, is called reachable, okay, is defined to be reachable from another marking. Remember that marking is just the values of all the tokens in the various places. So there is some other marking defined, denoted as MA. So MB is reachable from MA if there exists a sequence of transitions. So there, right, if there is some combination of transitions in a particular sequence, there exists a sequence of transitions from MA to MB, okay. So that is, so from M of T naught I can go to some other state after 2 transitions, and that could be, say, different possible combinations, right. There are so many transitions in the system, one or more of those can fire in whatever order. So T1 can fire, then T3 can fire, or T1 can fire, then T2 can fire if it is a 3 state 3 transition system, and so on, right. So but that is the definition of how you go from one marking to another marking, that is the reachability definition. So now we can extend this to define what is called as a reachability set. So reachability set, right, is a set of all markings reachable from some particular starting point, right. So is a set of, this is reachability set of a Petri net, as specified earlier, is a set of all markings that is reachable from M of T naught. So this is an enumerative process. How do I find this reachability set? You have to actually enumerate, right. So that is, we talked about in the last class, where you can look at all possible combinations of all, right, all the sequences have to be laid out, and then you keep on adding, right. So that is an enumerative process, it is exhaustive, but that is one way of finding out the reachability set, but that is the definition of this reachability set. So this is the set of all markings that you can reach from initial state M of T naught. Okay. So then we define a reachability graph, which is what I had drawn earlier. So a reachability graph, as the name defined, is this is a directed graph, okay. So the reachability graph for a Petri net is defined as a directed graph, where the nodes are, whose nodes are so what are the nodes for the Petri net for this reachability graph? All the markings, right, set of all the markings that are possible in that particular system, okay, all the possible markings otherwise reachability set, yeah, reachability set from whatever m of t naught, right. So this is the reachability set. So those are the set of nodes, and an edge exists from one marking MA to another marking MB if there is a if MB, or if there is a transition from one, this is not reachable, this is just immediate single transition. Reachable means there can be sequence of transitions, here it is only a single transition, right. So from MA I can go to MB if there is one transition that will take me from one to the other, right. So if I have written twice, if MB is reachable via a single transition, from MA, okay, and we label that edge with a transition name. Okay, so what I drew before, you can look at that as a CTMC only for a special case, but so the label of the edge is there, you simply label it with a transition. That is your basic reachability graph, okay, is it clear? So if you go back and look at the previous diagram, so here this is I talked about this being rates, for time being just ignore the fact that they are rates, but this simply says that this is marking 1, 2, 3, these are 3 possible markings, and the label on this edge is nothing but the transition that is used, right, on one of the 2 transitions, either T failure or T repair is what is being used to go from one to the other. I still have to define the rate, we will do that in just a second. So the reachability graph is just that, set of markings from m of t naught, and the label is simply the name of the transition that is used to go from one marking to another marking, okay. So this, now this graph if you look at it resembles like a Markov chain, right, it could be a discrete time, continuous time, we will get to those in just a second. So that is the basic notion of what a reachability graph is. Questions on this? So given any PN I can come up with this, only thing is you have to sometimes use a tool for automatically generating this, we can do it manually, but sometimes automation helps, right. So there are some tools out there which I haven't had time to try it. I downloaded something called Pipe, which can be used for with a GUI editor, you can actually draw those diagrams, draw all the labels and transitions and so on, then it will take care of giving you some of the performance results from that, right. It will construct the underlying, if it is a stochastic pattern, it will construct the underlying Markov chain and then solve that for particular performance results. So we will leave that as an exercise for you to figure out, okay. So now this is the basic notion of what a Petr net is, we have seen several examples of those. Now there are some extensions, right. So there are lots of different types of arcs and lots of different types of Petr nets also. So we look at some basic extensions, right, and see what those imply. Okay. So the first extension is we talked about arcs having, when I was saying that whenever a transition is fired, right, one token is removed from the corresponding input place and one is kept in the output place. So that is one. We can generalize by saying that instead of having, right, one necessary from each of the input places, we can make it some arbitrary integer k. So as long as there are at least k elements in a particular place, or only the corresponding transition will take place, right. So we can add no weights to each of those arcs. One on the input side, it says if I say input side I need to put a number 3, it means at least 3 units or 3 tokens should be there in the corresponding input place. If you put 5 on the output place, it means there 5 units are going to, 5 tokens are going to be added to the corresponding output place. That is one particular extension, and in some cases it is actually useful, so we will see how that is, right. So with the input and output arcs, it can be assigned some weight. We are used to link weights, right, so we will call this the weight, but technically they also call this multiplicity. If you have done UML, you probably remember that, right? In UML also you can specify, if you are creating an object, right, and one object is composed or composed of other objects, you can say how many multiplicity you can specify on those arcs. If you go back and look at UML diagrams, anyway, so that's what this is, right? Weight can be specified, which is an integer, non-negative integer, right, which is to be greater than 0, okay. And if the multiplied, if it is weight is not specified, so what we do is we write PNs, but we do not specify the weight, just leave the arc as it is. It means that default is 1, right. If weight is not specified for an arc, it defaults to 1. In fact, all our diagrams before have been implying that, right. I simply say that only one token can go, even though there are 2 tokens in the on state, by the transition I say that only one will go to the off state through that corresponding transition, right. So that is the first. So if you want to represent this, right, so let us say this is H, this is O. I think this example some of you might have seen. Right. So if I have 2 atoms of H, right, and one of O, you get a water molecule, right. Okay. So that is your H2O combination, okay. So that is how you can specify. We can of course generalize this to other examples that we know of, okay. Then there are something else called the inhibitor arc. Sometimes inhibitor arc is used to prevent a transition from firing in certain cases, okay. So this means that, right, if there is an inhibitor arc, then the corresponding transition, so inhibitor arc will end on a transition, right, it is input to a transition, the corresponding transition cannot fire, okay, if the corresponding input place contains at least as many tokens as specified by the multiplicity of that arc. So this means if I put 5 as the arc's value, so then as long as the number of tokens is less than 5, I will fire the transition, okay, at least one should be there, but if it is anything 5 or more, it cannot fire, right. Therefore that's that's again, you know, we will have to look at some examples where that can be actually useful, okay. It could be even 0, right. Okay, let us look at an example for the same. So if I define, so this circle at the end of the arc instead of the arrow represents an inhibitor arc, that's all, okay. So this is P1, this is P2, so this is the current state of the system, and there is another place P3, okay. So what will be the behavior of this system? So the definition is, if I do not specify the arc's weight, it is equal to 1, and by definition inhibitor arc will fire if the number of tokens is less than or strictly less than the weight of that arc, right. So at this stage, will this transition fire? Will the transition fire? No, it cannot fire because there is no, P1 is okay, P1 actually meets the constraint because it is empty, If it has got at least 1, I cannot do anything, I cannot fire, right. So I cannot fire at this stage because P1 is satisfying the condition, but P2 is not. We need at least 1 because I have not specified the token value, the weights on either of those two links, right. So therefore at this, in this stage it cannot fire. If I add another token to P2, right, then what can happen, then it will fire, right. So now the conditions are satisfied. If I have no token here and 1 token here, then I can certainly fire. So what will be the output, or sorry, the resultant of this particular system? Of course this stays the same, right. If I look at it pictorially, so there will be no token here as usual, the single token here is now gone, right, and how many tokens will we have in P3? 3. Okay, so that's our, so that is what this extensions of these arcs mean. So we will see when necessary we will use these, right, and so can we try to use this inhibitor arc to model our MM1B system? Morning we saw MM1B, right, I used this extra buffer. Can we try to model that with the inhibitor arc? How will we do that? Okay, so where will we place that inhibitor? Okay, I don't remember the exact solution, so we'll have to guess this out, right. So somehow I have to, there is some place here, right, which is holding packets, and I have to inhibit this from sending packets if this is right. So if it is greater than B, I cannot send it somehow, right. This is what I want to somehow capture in my system, right. I have to feed this to some transition. If there is less than less than B packets, I can forward it for servicing, right. If there is more than B packets, I cannot forward this for servicing. How will I capture that? So how do we model MM1B with the inhibitor arc? Can we somehow capture that? You need a transition before, okay, so let us say, okay, let us try to do this piecemeal. So I have the arrival process, right. So we didn't have an input before here or no? We don't have, so packets are getting generated here, okay. So then where does it go? It goes to the queue, okay. It goes to the queue here, then where will inhibition come? I have to somehow prevent this from firing, right, if it has got more than B elements in the queue, right. So that this packet has come and I want this to be added to this thing only, to this queue only if some condition is satisfied, right. What could that condition be? So let us say that I have another entry here, right, another place here, and I have that also as an input to this particular system, okay. So this will fire, right, and I have specified this to be say B if at all, right. I am trying to figure this out, this is probably not completely correct. So what will happen is this transition will fire as long as the number of items held in this place is less than B, right. If it is less than B, then what will happen, we still have to somehow process these things, right. So what I am putting this into this temporary buffer. So how will I do the processing part of it? So this has to go to some other transition, right, this has to go to some transition, and will this be the server transition or is it some other transition? So initially there is nothing here, packet comes in, it goes here, and let us say it gets serviced, right, and then therefore it simply leaves the system. Now the second packet comes in and I will put those 2 packets here, right, I can put 2 packets there, it is going to get serviced. Then third packet comes in, where will I put those? Somewhere I have to keep track of those token count, right. How will we do that? With this inhibition, somewhere I have to store those other packets that are coming. We saw a different way of doing buffers in the morning, right. So here how can we do that? We will leave this as an exercise. Okay. So keep thinking before the class ends. If you think of the answer, then you will include that. Okay. Alright, so these are some of the basic arc extensions. Now there are other extensions also. So far we haven't talked about this notion of timing present in any of these in the Petr Net itself, right. We said there are states or places, we said there are transitions, but there is a need to also bring in the concept of timing into the system for certain kind of models, okay. So there are different places in which time can be included in a Petr Net. So we will go through those and we will finally stick to just one of those, okay. So we saw the extensions, now let us look at a different kind of extension called the timed Petr Net extension. So the basic idea is to introduce time, the notion of time, okay. So time is introduced to model the interaction among activities considering their starting and completion times, because time is very crucial for a lot of the modeling that we try to do, right. It is not a static system, there is like every activity takes some amount of time, right. For example, processing a data packet, getting data from input output, right, all these things are getting out from the IO bus, all these things take time. So how are we going to bring that time notion into the picture? I gave a brief glimpse of MM1 earlier in the morning, right, even though we did not even talk about timing yet, there is implicit right time there, okay. So let us look at some things. We can introduce time in 4 different places. So one is called a timed place Petr Net, okay. So we can introduce the notion of time in a place, which means that, right. So what happens when a token gets added to a place, it will take some that it's like cooking, right, it's like getting put in the water, but the token is not ready for consumption until some period of time is elapsed, right. So maybe it takes a few milliseconds before the token can be considered as available for consideration for the corresponding next transition to fire, okay. So what we say is I could have a state, right, or a place which is feeding into a transition, and this itself in turn is fed by some other transition, okay. So there is some place that is feeding this into this particular transition, and when after a token is added to a place, it is not instantly available for consumption by the next transition, right. Even noodles takes 2 minutes to cook, so that is what, this is not really instant noodles, it takes some amount of time. So there are 2 kinds of packets or 2 kinds of tokens, right. These red ones can be considered as not available, not ready, okay, and the black ones can be considered as available, ready. So that is the time factor, right. So the the token generated in input place, right, becomes available only after some time, okay. So this is tokens. So when will it get generated? Whenever this transition fires, tokens are getting generated, right. So let us say that this is 3, right, the multiplicity of that. So the tokens generated in a place become available for transition only after some delay. That is called a timed place Petr Net, okay. This is only definition for now, we are not going to really use this, but if you look at it logically, I can add time in many places, and this is one of those places, right. So there is some time for this to become available. It is like, it's like trying to introduce some processing delay in a place itself. We normally talked about processing delay in the activity, but this is now saying that even within a place there is going to be some time delay, but it is not that much relevant to what we are going to talk about, okay. So that is one place. So where else can we add time? We can add time in the transitions and in the tokens, okay. So we will come to transitions, but before that we can also add time in the arcs. So 4 places I can add in the place, transition, in the token itself I can add, and then I can add delays in the arc itself. Okay, so let us look at timed token. Okay, so now tokens will carry a timestamp. So you create a token, then you put a timestamp, like we do with the packets, we do put a TTL on that, right? TTL says it has to be dropped by this time, right? This is little bit different, it says that it is available only after this time is elapsed. So token can travel, but it has got a timestamp implicitly built in, similar to this place business, but now the token itself can be, you can update the token on a time, the time on a token as it goes through different places. Okay, so tokens carry a timestamp, say theta I, okay, that indicates when they are available for transition. And as the tokens time can be updated, timestamp can be updated as it progresses in the system. Okay. At each firing that it encounters. So again pictorially, if we had, again we can sort of draw these things by hand, but somehow there has to be a system, right, that understands how to attach timestamps to tokens. So here is this thing, right, and then it goes to the next thing, and then it will have a an updated token on timestamp on that. So this, for example, this timestamp, the new token would be the old timestamp plus some delta I. That could be fixed variable, random variable. All these things are in theory possible, right? How is it going to be useful? That depends. That is we are not yet talking about that. But I can add the notion of a timestamp to a token. Is that clear? Now I can add times to arcs. This is like propagation delay, right? There is a link on this, and it takes a finite amount of time. Once a token leaves a place, it takes a finite amount of time for it to reach the destination transition. So there is a delay that is also incurred there, right? So therefore the travelling delay can be associated with an arc. Right, this is similar to propagation delay. On links, okay. So it is now possible, if you look at a transition, it could have several packets traveling on the transition. So let us say tau 1 is the delay, right, besides the weight that we normally specify. One packet could be here, one packet could be here, one token, right. Therefore along that wire different tokens can be traveling at different stages, okay. And likewise I can define something like this, right. So this is tau 2, and then it finally goes to tau 3 and P3. So I can also time the arcs. This could be useful for some cases, right. And that will make sense if you are looking at systems like pipelining, for example, or assembly, where it takes some time to move this part from one part of the factory to some other part of the factory, and that is a non-trivial time. It could take 5 minutes, 2 minutes to ship, and that is also has to be considered in the total delay of the system, right. It is not just the processing time, this travelling delivery time is also crucial. Okay. So now that is timed arcs. So now we will come to our timed transitions. And timed transition is something that we can quickly all relate to, okay. So transitions represent an event or an activity, right. It's some processing things going on, event or activity. That is what the transition represents. Okay. So then we define the, so then activity, right, start. So there is a notion of a transition getting enabled, which means that it gets started, but then the actual firing of the transition will take place some tau units later on, right. So transition enabling means the conditions are met, right, starts when the right transition is enabled. So all the preconditions are met, right. And we do not worry about what happens if the conditions change, right, in between the before this transition completes. We assume that the those conditions still hold, okay. And the activity ending time, basically when that processing whatever is complete is when technically the transition firing time. So there is a gap between enabling the transition and firing the transition, okay. That is what this is. So there is so this is time, this is the enabling of the transition enabled, and then transition is now fired. So that has to come into the picture, okay. So this is the so called transition, timed transition, okay. There are different types of firing. We will just, there is something called atomic firing, which is what is used. We will for now just not worry about that detail, because that is the sort of default thing that we will talk about, okay. So now we come to the special class of timed Petri nets called stochastic Petri nets. Okay. So a stochastic Petri net or SPN is a timed transition Petri net, okay, where with atomic firing and all the transition delays, okay, all the delays associated with all the activities are distributed with some well known random variable distribution, and what might that be? Exponential, right, or convenient. So all the transition delays are negative exponentially distributed or exponentially distributed. So that is a special class of Petri nets. So it includes delays for transitions, and the delays are all distributed with some exponential distribution, okay. And there is also another class called GSPN or generalized stochastic Petri net, okay, which is basically stochastic Petri net with two kinds of transition delays. One is instantaneous firing and one is exponential time firing. That is what is called as a generalized stochastic Petri net, okay. So this is a stochastic Petri net with both instantaneous, right, firing, instantaneous transitions and exponential delay transitions. Because sometimes in a system you will find that there are some activities that are just instantaneous, there is no need to delay them at all. It is like some things are just take almost negligible time, so you can consider that as mirror transitions, okay. Okay. So questions? Questions? Okay. So now when I define my SPN, so to define the SPN, we need the same things as before, the set of places, set of transitions, your I, your O, okay, and then your M naught is also needed. In addition, you need your W. So W is the set of, this is simply, right, W is a function, or this is basically the set of all transition delays, the transition rates as we call that, okay. So because when we talk about exponential, we talk about mu parameter, right, exponential is mu e power minus mu x, where mu is your rate, we call that, that is the rate of the rate parameter for the corresponding distribution. So therefore this W will specify, this is a function defined on the set of transitions that associates, the function defined on the set of transitions that associates each transition with the rate, okay, and this rate is nothing but the inverse of the mean firing time, right. If the delay is exponentially distributed, it has got the mean value is 1 over mu, right, for when we define it as mu e power as the mean firing delay of a transition. Okay. So if I define, right, mu e power minus mu e power minus mu t, right, this is our definition of the transition time t greater than 0, and right. So this is the probability of right, this is our probability function, and we know that mu represents the rate and 1 over mu represents the mean time that is spent in a given transition, mean time to fire a transition, okay. Questions on this? No? Okay. So why are these stochastic Petr net special? Because the reachability graph of stochastic Petr nets are isomorphic to the state transition diagrams of continuous time Markov chains, also called CTMCs. So I can take a Petr net in SPN, derive the reachability graph, and from the reachability graph I can derive the corresponding CTMC. Once I get the Markov chain, I can simply solve that by all the techniques that we have seen before, and then once I solve that, I can find out the probability of a given state system being in a given marking, and then use that for getting throughput delay and all those various possible calculations, okay. All right. So let us look at some sample values, okay, and see how we can do this. So here is an example of stochastic Petr net. There is a place P1 and there is a transition that it feeds into T1. The rate of this transition is lambda. Then there is another place P2 which goes to another transition that goes to another place. Rate of this transition is mu. This goes to one more transition called T3. We will call the rate of that as that, and then there is a feedback loop here. Okay. So this is our sort of classical, right, closed queuing network. We will impose the condition on this that there is only one token in the system at this. There is only one token. No token generation is possible. So I start the system by placing one token in anywhere P1 or P2 or P3. Okay. There is only one. This again this system's right specification. Only one token. I can make this multiple tokens, it is not a problem, but for now we will say that there is only one token in the system, because that is easier to set the state space, otherwise there will be too many state space combinations. Okay. In fact, we saw this when we did mean value analysis and those extensions, right, those different techniques that we saw. Okay, only one token in system, and the M of T0 is simply 1 in P1 and none in the other two. Okay. So now what happens, there is a token available, these two transitions will not fire, this transition will fire, and the mean time to firing is 1 over lambda, right, this is exponentially distributed. So after the time the token will get transferred from here to here, then it will spend some time here, it will get transferred and so on. This is like going through a sequence of 3 servers, right, 3 MM1 servers, where each server service time is given by this lambda, mu and gamma parameters, right. So this is the SPN specification. Okay. Now how do we translate this to the CTMC? Okay. So the state of the system is defined as a 3 tuple, okay, because CTMC requires states, right. So how do we, what are the states? So state of the system is basically the marking, right. So if you look at the as the marking value, right. So what are the possible marking values? The marking values are 1, right, 0 0, then there is another one which is 0 1 0, and then there is 0 0 1, right, because there is only one customer, one token in the system at any point in time. These are the only 3 possible states, 3 markings, and the rate of transition from here to here is lambda, rate of transition from here to here is mu, and the rate of transition from here to here is gamma. This is my CTMC, right, and then I can solve this whichever way I want to quite happily, right. I can solve and find out what is the time that is spent in, right, in each of these states, what is the probability of spending time in this marking, in this marking, this marking, and then you can do some sort of delay analysis in the system. How long does it take before a packet that token that starts here comes back to this, right. Basically when we come back, that means that all the three servers have been dealt with, you have been serviced by all the 3 servers, come back to a starting point. That in essence defines the throughput of the particular system, right. Okay. So probability of being in this state times this lambda, which is the rate of that particular thing. Okay. So questions, clear enough. So if we can again apply this to our other model that we saw before, right, the model with the failure, that on off situation, right, where I can see if I say the same thing as before, I have this is the on state, and there are 2 tokens to start with, and then this will be, right, this will trigger, and so again if I say that the failure rate is lambda, right, this is a transition failure, right, so T failure transition. So then we go to the off state, then the mean time to repair is mu, this is the other transition, right, it simply goes like this, right. So this is the for this particular system, right, what will be the corresponding CTMC? What are the possible states for this system? We saw that before, right, 3 states are possible. So it is given by 2 comma 0, 1 comma 1, and then 0 comma 2. So if you want to find out what is the fraction of time both the system, both these machines are operational, right, I simply need to find out the steady state probability of being in this state, right, and what is the fraction of time that both of them are down, that will be the steady state probability of being in this state, right. So what are this? So from here to here, what will be the rate of moving? Lambda, and then from here to here, rate is again lambda, from here to here it is mu, from here to here it is mu. That is your corresponding CTMC, and this, if you remember, is like our MM1B system, right. MM1, this is like MM1-2, where there are at most 2 packets in the system. We can very easily solve for this corresponding transition probabilities. We will do one example at the end, right. In fact, even here we can try to solve the corresponding transition probabilities, right. So how do we solve the transition probabilities? I want to find out the probability of being in the state 2 0, let us call that, since we call this is right, so this is P1, these are 3 states, right. So let P1 be the steady state probability of being in state 1, P2 of being in this state, P3 is the probability of being in that state, right. So can we write the corresponding balance equations? So what will that be? So lambda P1 equals mu P2, right, and then lambda P2 equals mu P3, because this is the probability of being in P1. So the rate of leaving is lambda into P1, the rate of entering the state is from P2 I will enter to the state, rate is again mu, probability of being in the state is P2, therefore this is lambda P1 equals mu P2. Likewise lambda P2 equals mu P3, right. These are the 2 equations that we have. Any other equation possible? We only have 2 equations, right. So can we solve for P1, P2, P3? How will we do that? So let us express everything in terms of P1, right. So what is P1 equal to? So lambda mu1 equals, sorry okay, so lambda into P1 equals mu into P2. So if I express P2 in terms of P1, what will that be? P2 equals lambda by mu into P1, and then we said lambda P2 equals mu P3. So what will that give me? P3 equals lambda by mu into P2, which is again lambda by mu squared into P1. So I have expressed P1, P2, P3. Now can I solve? How will I solve and get the values for P1, P2 and P3? I still need one more equation, right. I have 3 unknown variables, and what is the third equation? They all add up to 1, right. I said these are probabilities. So P1 plus P2 plus P3 should equal 1. So now we know that, right? So therefore P1 is going to equal to 1 plus lambda by mu 1 plus lambda squared by mu squared to the power minus 1, that is my P1. So therefore the probability of being in steady state in the system is just that, 1 plus lambda by, right. Okay, and if you want to plug in values, let us say lambda is mean time to failure is, let us say 10, right, because that we want this lambda to be very large, we want the mean time to failure to be fairly large. So let us say that equals 10, and I want repair time to be fairly small. So let us say that mu equals 2. Therefore what will be P1? 1 plus 5 plus 25 to the power minus 1. So 1 by 31 to the power minus 1, is that right? No, 1 by 30, 1 by 31, right. Is that right? That seems to be right. So probability of being in a system where both the servers are operational is actually only 1 by 31. Is that high or low? That looks pretty low, only 3%, right. And why is that? Because our lambda value is so large, right. So, so what should happen here? So I want my lambda, if my lambda is even 1000, then what will happen? It seems to be even worse. That does not seem right. I want lambda to be very large, right. So the mean time to failure is very large, then what will happen? What should happen? The system should never even go to 1 state, right. Sorry, this is the okay, yeah, lambda equals 10 means that the mean time to failure is actually 0.1, right. So lambda should be very small, right. So that means every 0.1 units of time on average I am going to fail, and that is not a particularly good scenario. Okay, so we will have to go back and rework this. So I will pick some small value for lambda, right. So which means that the time to fail, right, the mean time to fail is 1 over that, which is 100, and I can pick again mean time to repair also should be small, right. So if I want the mean time to repair to be say 10 units of time, so every 100 units of time I can fail, but I want the repair to happen on average with say 0.1, right. So, mean time to repair should be 0.1, therefore, mu should be say 10. In that case, then you will find out that lambda by mu is fairly low. So, rho is low, right. We remember this MM1B, what happens? We want rho to be, if rho is very small, what will happen to rho MM1B? What state are you going to be in? P0, right, where the system is mostly idle. The same interpretation, but here it is not idle, it simply means that both the servers are essentially operational. So, you want to be in P1 in this particular case to the extent possible. Okay. So, P1 is now 1 plus 0.001 plus 0.000001 inverse, right. So, therefore, that is a very small addition to 1, therefore, this kind of going to be hopefully close to 1, right, some small value. So, that is how the representation from the PetriNet side converted to CTMC side, and you can get the corresponding. Now, you might ask, why should I go to say PetriNet to actually do? I could run this straight away with the Markov chain. You could have, but that is okay, right. You wanted to show an example of how you go from one to the other, but sometimes systems can be very complex, right, especially concurrency is not directly captured in a Markov chain, right. So, you will have to capture concurrency with the PetriNet and then translate the states into what we do here, right, and so that is where the potential benefits of this particular system are. Okay. So, question, any questions? Okay. Okay. So, now let us look at another sort of similar example. Only thing is, this will come to this, we will again look at the notion of conflicts, right. So, there is one state P1 which is getting fired by a transition or connected to a transition, then from P2 so transitions T2 and T3 are again defined by the corresponding exponential delays parameters mu and gamma. This goes to another state P3, we will say, this goes to another transition T4, and this is with some parameter delta. After that I come back here, and from here I go to P4, from P4 I get connected to transition T5 and say sigma is the parameter, and I come back here, and I can start this system. I can start the system with 1 token, 5 token, does not matter, right, any number of tokens I can have. So, now what do we see here? This is, I can also represent this. Now, there are, let us assume that there is only 1 token in the system as such, only 1 token, and it moves among these processes like n equals 1 in the MV analysis that we have done earlier. Okay. So, what are the possible markings of the system now? How many possible markings are there? There is only one packet, right. So, it is either in P1 or P2 or P3 or P4, so only 4 combinations, right. So, just like before, so this is just repetitive of what we have done before. So, 1000 represents the state where the token is in P1, 0100 where it is in P2, and then and so on, P3 and P4. Okay, and here is lambda. Okay, let's there is a transition from here to here, right. This is with rate mu, this is with rate gamma. From here we come back, and from here we come back with the rate sigma. So, here there is only one catch, right. What is that catch? Did anybody get that? I can go to either T2 or T3, right. When there is only one token in P2, which of these two transitions will get fired? we do not know, right. There has to be some other information, either it is random or some priority based information has to be provided. This is, remember, what the system does it look like? Does it look like any system you have seen before? You have seen this like lots of times in class. A CPU 2 disk, right. This is one CPU and 2 disks. So what happens, the process gets processed in P1, which is the CPU is represented by T1. After processing, it can go to either disk, this disk or this disk. After processing in that disk, it simply comes back to the CPU, right. This is a one CPU 2 disk representation, and the notion of probability has to be now brought in, right. So the state transition matrix will now also include the rate as well as the probability of that rate, okay. So we can, this is something that we can, if you are going to, so what is the probability of going from P2 to either P3 or P4 when the service times are defined this way? Do you know what the probability of, what will be the rate going from this to that? It will be mu by mu plus gamma and then gamma by gamma plus mu, but that is something that we can derive, but anyway that is one thing that we wanted to talk about.